Welcome everybody. This is OpenCV weekly webinar, and today we are going to cover how to create a panorama. We'll go into the theory as well as an implementation. And with me is Bill Kromydas, who is one of the instructors on OpenCV for Beginners, and you will hear his voice explaining notebooks on OpenCV for Beginners, which is our new course. Actually, Phil can go ahead and share the link to OpenCV for Beginners Kickstarter once again. It is a Kickstarter we are doing for a new course. It's a short, fun, and affordable course for beginners, those who don't know. And Phil, as always, he is, let me actually finish. I'm sorry. Bill has a degree, a master's from MIT, and he's one of those people who made a transition from the aerospace department into computer vision and machine learning. So that's something exciting. Bill, would you like to add anything to that introduction?
Well, thanks, Satya. No, I'm glad to be here. I've always really been interested in machine learning and computer vision in the last 10 or 12 years, and spent a long time in the space and defense industry, and finally decided to make a transition, and really enjoying it. Thank you.
And people ask me, all the time that, do people get a job after taking your courses? And Bill actually took deep learning with PyTorch. I don't know whether you took computer vision for faces as well, which was a very old course we did.
Right, I signed up for that a while back, and then I backed the Kickstarter in 2019, and yeah, I really enjoyed it. Thank you. Yeah,
so people do get jobs. All right. So Phil, as always, Phil is our content manager at opencv.org. Phil, any words from you?
Just, hey, everybody, thanks for joining us. Thanks to those of you who joined us a little bit early today for some extra Q&A. At the end of the show, as a reminder, we'll be doing a trivia question, and you will win a free pass for CV for Beginners when it drops, and CV1 from OpenCV courses. So stick around for that.
Yeah, as always,
we'll ask
a question.
At the end of the show.
We'll ask a question, and if you're paying attention to the webinar, you will definitely understand, you'll be able to answer that question. So let's get started. Bill,
should I share my screen? Sure.
So the way we are going to do this is we are going to tag team on this one, and I will explain part of the notebook, and Bill will explain part of the notebook.
Finally, my pro wrestling t-shirts are rubbing off on Satya.
Right. Okay, so let's get started. Now, the objective here is to teach you everything that's needed for creating panoramas, right? And as you know, panoramas are images that you basically stitch images together. So we will learn the math, what is required, and we will understand how to do it in OpenCV. We will go over the technique first, which will be, very detailed explanation about the various steps. And then we will say that, don't worry about any of those things. You can write like these 5 lines of code, and OpenCV just does it for you, right? But let's first understand the technique. And for doing that, we'll learn about image alignment first. And image alignment is basically this idea that we have 2 images of the same object, right? And in this case, the object is a plane. You can see this form where you're looking at this arrow, and this form needs to be aligned to a template. Just imagine that you're taking a picture of a check, or you're taking a picture of a form, and you have a PDF of that form, and you also have a filled out version of this form. And you want to align it to the PDF so that you know which areas you have filled out. So an application like that. For that, you would use this technique called image alignment. And let's go over what it takes to do this. So let's go over the theory first. To understand this thing, we need to understand something called an image transform. How can you modify an image using different image transforms, and what do you get? Now, let's say you have an original image, and we are representing this original image as a square. And you can also think about this, that you have an image, inside that you have a picture of a square, okay? The simplest kind of transform you can do is called translation, which means that all the pixels in the image are moved in X and Y direction, right? So you can see the translation is the movement of that square by X and Y. You can also do something called a Euclidean. In OpenCV jargon, it's called Euclidean, but Euclidean is simply translation plus rotation. So you rotate the image and you can also translate it. So the combination of the two is called Euclidean. Now, for a square, see that the angles are not changing. Right angles remain right angles because it's a pure rotation. A more advanced kind of transformation is called an affine transform. An affine transform is Euclidean plus shear. So you can see that the 90-degree angles no longer remain 90 degrees, right? They actually have changed in angle, but parallel lines remain parallel. So that's the property of an affine transform. And if you think about the number of parameters it has a translation, 2 parameters for translation, X and Y. Then we have 1 parameter for in-plane rotation, how much theta it has. And then we have 1 parameter for shear, right? Which tells you how much shear has been applied to one of the sides, right? Now, and then there is also scale. I was missing something. I thought, where are the other 2 parameters? So there are 6 parameters in all. Rotation, translation, 2 parameters for translation, 1 parameter for shear, and 2 parameters for scale. You can have different scaling in X and Y direction, right? So that's affine transform. But the last transform is interesting. It's a homography. And this is what we will use for image alignment. This is also what we use for panoramas. So in homography, you can see that the image, which was originally a square, it gets transformed to an arbitrary quadrilateral. So you can pretty much get any image to be any quadrilateral. But it's still not 3D perspective. You have to keep this in mind, that this image is not 3D perspective because a plane, we started with a square, which was a plane, and then you can transform it to any quadrilateral. Homography is somewhere between, affine and a full 3D perspective transformation. And it has 8 degrees of freedom. One way of thinking about those 8 degrees of freedom is that all the corners, if you look at the 4 corners of the square, they can move anywhere. Each corner has 2 parameters, X and Y coordinates, right? So homography has those 8 degrees of freedom, and therefore, it has 8 degrees of freedom. It has 8 parameters that define it. Now, let's move to the next slide. So the question is, in a real image, how do we define a homography, right? How many points do we need to define a homography? It turns out that homography, when you represent it, this transformation, it is represented as a 3x3 matrix. A 3x3 matrix, as you know, would have 9 elements. But as I said, that homography has 8 degrees of freedom, which means that 8 out of that 9 elements are used, and the last element is 1. So if you use OpenCV and you actually print out the homography matrix, you will always see that the last element is 1. The way homography is defined between 2 images. Now, physically, let me give some physical interpretation of homography. So we are looking at 2 images of a book, right? This is 1 image, and then you move the camera and took another image. Alternatively, you could have kept the camera static, and you could have taken 2 images of this book also. Let's say you have this, you have this book, and from this camera, I take 1 image and I take another image. All the points in this book, on this surface of the book, which is a plane, they will be related by homography in the 2 images. Now, let me explain a little bit about that. Let's say this yellow point, I don't know whether you are, is it possible to zoom in?
Yeah, let's take a look. try. Is that better?
Yeah, that's better. So you can see that there are these, points, a yellow point, a red point, an orange point, and a green point on the book. We have marked it using, using a dot. These points are corresponding points. This is the corner of this. This is the corner of this side, and we have marked these points. These 4 points, if you mark these 4 points and get the coordinates of these 4 points, you can estimate the homography which maps, one point to the other, right? So homography is between. So another way of saying this is that a homography is defined by 4-point correspondences. So if we know the coordinates of 4 points, the XY coordinates of this, the XY coordinates of this, and we know this for 4 coordinates, we can calculate the homography matrix, the 3x3 matrix. And once you calculate the 3x3 matrix, you can apply it to this image on the right and get it to align with all the images, with this image. Now you may be asking, what happens to the other parts which are not on the plane, right? This part is not on the plane. They will not be aligned. So homography is only defined for a plane and the planes from which we have extracted the points. So if you have 4-point correspondences, we'll be able to extract that homography and align these points. So now Bill is going to show us what I just mentioned, how we do this. Let's go ahead, Bill.
Sure. Okay, so let's take a look at the code that implements all this. So in this first cell block here, we're just importing some required modules. And then the very first thing we're going to do is read in both images. So here we're reading in the template form and also the scan form. And we're reading them as color images. And notice that there's a line right here that converts the channels from BGR to RGB. And that's because OpenCV uses a BGR convention. But
Bill, if you don't mind, could you make it even larger, even broader?
Okay.
So that people can see it.
Is that better?
Much better.
Okay.
Yeah.
So, right. So just mentioning that if you're not aware, OpenCV uses a BGR channel format. And to properly render these in the browser, we need to convert that to RGB. So that's what we're doing here for both images. And then we're simply going to display the images down here below. So we've already seen this above. And the goal here is to then find corresponding points between these 2 images so that we can compute a homography and then transform the scanned form to the right into the coordinate space of the template form here to the left. So let's scroll down a little bit further and talk about the second step here, which is finding key points in both images. So the first thing we're going to do is convert both images to grayscale. And then we're going to use this.
Bill,
yeah,
here?
sure.
Yeah. So one thing I wanted to mention is that you could go ahead and click on 4 points on the 2 images and find correspondences that way, right? So which would, and then find the homography using find homography method. But we want to automate the process, right? To automate the process, we need to find these interesting points, which we call key points. Go ahead, Bill.
Okay. All right. So so to do what Satya just mentioned, we're going to use this orb create class to create an orb object, and that's going to give us access to this detect and compute function where we can pass in the both images in grayscale and get back a list of key points and descriptors. So the key points are well-defined, usually sharp corners or edges in the image that are defined by a XY location, a size, and an orientation. And then the descriptors are essentially a feature vector of the pixel area, pixel patch, in other words, around each key point. And we actually use the descriptors to match up key points. So what we get back here from this function call is a list of key points and the corresponding descriptor vectors. And then in the image below here, we're just going to render, we're going to use this draw key points function to render all those key points. So you can see here on the left-hand side, we've got several key points. And also on the right-hand side, notice that there's a lot in the right-hand image that don't even appear in the left-hand image. All these key points here in the center of the scanned image are not even over here on the left-hand image, but there's plenty of key points in both images that look like they correspond to the same point in both images. So the goal here is to proceed from here and try to match up these key points. And then we're going to use those key point matches to compute the homography. But one thing we wanted to do just real quick here is I think it'd be instructive to print something out here. Let's print the descriptor. So we can do that.
I would also like to add one little thing here. Now, key point and descriptor, this kind of separation is often done in computer vision. Now, if you are, when we try to do face recognition, for example, we first detect the face, and it doesn't matter whose face it is. We want to detect interesting regions in the image, right? So face detector would detect interesting faces or uninteresting faces as well. It will detect all the faces in an image. And then if you want to recognize that, then you use the features of the face to do the recognition. Similarly here, we detect interesting areas of the image which are good feature points, okay? And then because we match two features across two images, we also need a descriptor for that. We want to recognize the features in one image and the other image. We want to match these things. So we want a descriptor for it, which means that it's almost like recognition. You want to recognize this, this feature. So let's look at what the descriptor looks like, right, for this, for some arbitrary feature.
Right. So we just printed out the descriptor here. So this is a vector that contains information related to the pixels in the region right near that key point. And the descriptor is simply a list of unsigned integers here. But if we want to take a look at the key points, that's actually a data structure. And so you can't simply print out the key points. You'd have to know what that data structure looked like. But you can go to the OpenCV documentation, and I'll just bring up the page right here and search on detect and compute. And I did that already. And if I click on key point here, then that's going to give me some information about what that data structure looks like. And you can see here that some of the elements in that structure are the angle, which is the orientation of the key point, the point, in other words, the XY coordinates for it, and also the size. So with that knowledge, I can now add to this print statement here and actually print out both the descriptor and the key point for the very first key point. Notice I set the index to 1 here. So we're going to print out the key point and the descriptor for the first key point. So let's take a look at that. So you can see that it's got an angle of 164 degrees. The size is 31, and then it's located at 31,107 down here in this image somewhere. So of course, it's one of these red circles down here in the image. And we'll take a look at that in a little bit more detail further below. So let's go to the next section here. And so now we're interested in matching these key points.
One other thing I wanted to point out in that image. So each circle is a key point, obviously. The line in the circle, if you look at that line, that represents the angle of the key point. And when we calculate the descriptor, that angle is used so that the descriptor is consistent, no matter what angle you want to recognize the same descriptor. So that angle is used for calculating the descriptor. And the size of the key point is represented by the radius of this circle. It doesn't matter actually for us. It doesn't matter, these angles, etc., because they are internally used to calculate the descriptor. Now, if you want to match 2 points, the descriptor, 2 points, the same key point in 2 different images, the descriptor should be the same, right? That's how the descriptors are designed, that even though we are looking at 2 different images, they remain constant. They should look the same, and we'll see that.
Okay, so in this next section here, we're going to now attempt to match these key points. And to do that, we create a matcher object using this descriptor matcher create class. And that gives us access to this match method. And we simply pass it the 2 descriptors. So descriptor 1 and descriptor 2 for both images. And that's going to return for us a data structure that does a brute force matching on these 2 sets of feature vectors and gives us back several quantities in this data structure. One of the quantities would be the some distance measure between the 2 feature vectors. as well as the indices associated from each list so that we can actually make the correspondences. And then one final step here is to take all these. Well, then we sort the list. So now we have the first match in the list is the best match, and then it goes down from there. And then what we do is we prune that list to the top 10% of matches. And so this 10% is a configuration parameter you can experiment with, but in this example, 10% works fine. And then next here, we're going to just draw those matches and render that information on the screen. So we call this draw matches function. And this takes as input image 1 and the key points for image 1, and image 2 and the key points for image 2, and then the matches data structure. And then with that, we can display both images again, and we're drawing lines now between the sorted list of matches between both images. So all these lines that are, for example, take a look at this this region right here. I don't know if you can see where my mouse is pointing, but there's a icon here of a house, and that house has several well-defined key points associated with sharp corners and edges in that house, and those have been associated with the same region of the image over here on the scanned form. So notice that we're drawing lines from those key points to these key points, and those are good matches. Notice, however, that there's other matches that were computed that are not correct. So this line down here in the lower left is going up to the upper left of the scan form, and that's obviously not a correct match. It turns out that the feature vector for the key point on the left image and the feature vector for the key point on the right image were relatively close, coincidentally, and so that's why that match was considered. But obviously, we know that that's not a good match. But what's important here is that we do have a lot of good matches, and we'll see below that we're going to now use an algorithm to find the homography. And we're going to use a method called RANSAC, which stands for Random Sample Consensus. And that's a very robust method for throwing away outliers from this collection of key point correspondences so that we can then compute a homography that makes sense between these two image pairs. Satya, was there anything you wanted to add? Yeah.
Yeah, I'd like to pause here just to summarize, where we are, because a lot of people here may be beginners and they may be getting lost in what are the various steps we are taking. So just to summarize what we have learned until now, we learned that a homography, it has 8 degrees of freedom and it can match any plane to any other plane. So if you have all the points on this on the surface of this book, I take 2 images, all the points on this first image are related by all the points in this image by a matrix called a homography. And now, if we find the homography, then we can warp the image, the second image, to align with the first image. And what do we need to find this homography? We need 4 corresponding points, right? And we want to do that automatically. Now, 4 is the minimum required. If you have more corresponding points, we'll use all of them. We will have a more robust estimate. We'll have a better estimate instead of just using 4 corresponding points. For that, we estimated key points in both the images. So, and a key point has both a location and a descriptor. And using the descriptor, we matched the key points in this image to the key points in the second image. That's what we have done so far. And most of the matches look good. They are very nice. The key points have matched really nicely. However, it's also possible that there are several key points which are mismatches, right? So we have to use something which is very robust. Now I want to see, Bill, if you could show us, what do these matches look like, right? When the descriptor matches.
Yeah, let's take a look at that. So we'll start by just, so I just added 4 lines of code here to the cell block here. So this was where we did the matching, okay? And so the matches data structure contains all the information for how these key points correspond to each other in two different images. And so we can start by just remember that for each key point, there's an associated descriptor. So what I'm going to do here is plot what that descriptor looks like for the very first key point from both images. Okay, so let's just take a look at that plot. So what this is the descriptor for key point 1 in image 1 and the descriptor for a key point 1 in image 2. So these two feature vectors don't look like they line up very well, and that's because the first key point in image 1 is not necessarily correspond to the, we had to do the matching to figure out which descriptors go with each other. I just hard coded this to index 1 from both images, and we kind of get a plot here that doesn't look like these two descriptors go with each other, and they don't. So what's more informative actually is to use the information that comes back from the matching to take a look at that. So I'm going to add one more cell here. Okay, so I just added another cell here. It looks very much like the one above, except instead of using the same index into both descriptor vectors, I'm passing in the indices that are associated with the match. So the matching function to determine that, for example, key point 7 in one image goes with key point 22 in the other image. That's what this mapping does. So if we then take a look at this, you'll see that these two feature vectors line up very nicely. So this is actually the top match. I set index to 0, which means it's remember, it was a sorted list of matches. And so that's the top match, the one with the minimum distance between those two feature vectors. If I take this and create a similar cell down below, let's take a look at that.
So one thing to, if you're a beginner, one thing to keep in mind here is that you will never get a perfect match, right? Because these images are not perfect. There is pixel, the pixels have quantization. It's a pixel. It may not match exactly, right? There is noise in the image and all kinds of issues. So this is a very good match, right? When you see something like that, the two curves are overlapping. That's a very good match.
Okay, so that's the top match. Let's take a look at the last match in the list. So this should also be quite good, but not as good as the top. So here there's some number of matches, and I'm going to the end of that list and going to print out the difference between those two vectors. And you can see here that it's pretty close, but certainly not as close as the top match. And both of those are much better than this random match that we performed up here by just not taking advantage of the information from the matching function. So we thought that was just instructive to take a look at that. And then
people are interested how the matching is done. It's a brute force match, which means that you have two vectors that we had seen in the before. And these are, I don't remember exactly, maybe 20 element vectors. And you just take a difference of them, sum of squared differences, and then sum it up, right? So you take the element-wise difference, square it, and sum all those things, and that will give you the distance between these two vectors. So you could do that. That is one kind of distance. Another kind of distance would be you take the absolute value and then sum it up. So there are these various distance measures, but there's nothing fancy going on in this matching function. You have two vectors. You want to find how close they are to each other. You find these distances and see which one is the closest, and then you return these matches. So nothing complicated going on.
Okay, and then so let's see. We did talk about this already. This is just rendering the correspondences, and most of these look like they're very good. There's a few outliers. As anything that's not parallel looking is going to be an outlier. And then now we're ready to compute the homography. So we do that using the find homography function, and that takes as input two sets of key points, and then also an optional argument which indicates the method by which we're going to compute the homography. And we mentioned that earlier. It's RANSAC, which stands for Random Sample Consensus. The code just up above here is simply, so notice that we're passing in points 2 and points 1, these lists. So we start with the key points, and then we use a for loop here to actually use the results from the matching function so that we use the correct index for both lists. This way, we're passing in the correct set of points to the find homography function. And then here's a little bit of code, which I'll let Satya talk through. It just, now that we've got the homography, which is H, we can use that just to confirm that it's working properly by using that to transform a point from one image to the other. So go ahead, Satya, if you want, and I'll scroll through here.
Yeah, could you just scroll a little bit up, like a one line? No, in the other direction. Yes, one line up where it shows ransack. No, sorry, down the other direction. Yeah. Go to the start of the code where it says 00, right? Not 24. Right now we are at 20. Yeah, that's perfect. So you can see that in the top line 10. Bill, can we go to line 10? Okay, yeah. Great. In line 10, we find the homography, right? And what do you need to find the homography? As I had mentioned before, you need the set of points, minimum 4. You need 4 points in this image and 4 corresponding points in this image. So we did the matching, we found the corresponding points. They're not perfect. Most of them match, but there could be some outliers, right? To deal with that, we use a technique called ransack, cv2.ransack. If you have time, we'll go into ransack, but just assume that ransack is a method that allows us to estimate parameters when there are outliers in the data, right? You can imagine that if you had a bunch of points which form a line, and your goal is to find the parameters of the line, a single outlier can completely destroy your estimate of the line. You know, the line you fit through this data is usually trying to minimize the distance between each point and the line. But a single point, if it's very far away, it can tilt the line estimate and completely destroy your estimate. For such cases, we use, and this kind of point is called an outlier. For these kind of things, we use something called an algorithm called ransack, which is a clever way of throwing away this outlier, right? And if you have time, we'll go into it. But for now, just remember that ransack is used whenever we have noisy estimates, okay? So, okay, we have 2 sets of points, and we found this homography matrix. And if we print the homography, so the first line, in line 13, we are printing the homography. And as I said, after line 33, you can see the results of that homography, right, of that printing. And as you can see, it's a 3x3 matrix, and the last element is 1, because, you know, we have only 8 degrees of freedom. Now, the other parts are complicated, but there are things that you can learn from this matrix. One of the things is that the last column, -4, that piece, basically it's the translation of the image. And if the image doesn't move at all, this would be a diagonal element. You know, it would be a diagonal matrix of identity. You know, it would be an identity matrix. The top left-hand side, the 4 elements, they represent, you know, scale, translation, not translation, scale and rotation. It's a combination of scale and rotation that determines those things. The bottom row basically encodes additional information beyond the affine part. So the important thing, it's not very crucial to know what each and every element does, but let's see what this homography does for us. Okay, so the next thing is that we are printing out the first point. Okay, this is in the template image. We are printing a point in the template image, and then we are printing the same point. It's the matching point in the scanned image. So in the image, second image, and then you can see that this matrix cannot be applied to this 2x1 image, 2x1 point, right? This is a 2D point, and this is a 3x3 matrix. You cannot multiply them. The reason this matrix is 3x3 is that we use homogeneous coordinates for doing the calculation. And homogeneous coordinates is nothing but you take the x and y and then append a 1 to it. I don't want to go into, you know, the details of why we do that, but just keep in mind that it makes the math easier. It makes it everything in terms of matrix multiplications, and it makes the math easier. But now we have this vector, right, which is 172, 631, 1, which we got by simply appending a 1 to our previous point that we had got. If you multiply this, matrix multiply this point, 172, 631, 1, to the homography, you will receive a point which is 105, 532, etc., right? And you can see that this, again, this has the last element is actually not 1. So we have to normalize it and divide it by the last element. So all the elements we divided by the last element to normalize it. Now we get something which is 97, 482, and 1. If you compare this point to point 1, so they are very similar. So point 1 and this point, which is the normalized homography, homogeneous coordinate for point 1, they are very similar. And I rambled on a lot. Let me summarize what we did here. We took point 2, which was a point in the second image. We changed it to homogeneous coordinates by appending a 1. We transformed the point by multiplying it by the homography. And what we received was a point in homogeneous coordinates, which we could transform by just dividing the last element. And the point we got is a transformed version of point 2. And what we found is that this transformed version of point 2 is very similar. It's almost the same as point 1. So what homography did is it transformed this point 2 to point 1, right? And that's exactly what we wanted, right? We wanted to find this 3x3 matrix, which when applied to a point in the second image, gives us the point in the first image. And that's what we have achieved here. I'm sorry if I rambled a lot, but if you look at this, we'll share this notebook with you, and you will be able to play with it and see what exactly is going on. But for now, the only thing you need to understand is that you can transform points in the second image by applying a homography. And when I say applying a homography, you're literally multiplying the homography to this point, and you can get back the original image, the point in the first image. Now, when you do this, it also means that you can apply this homography to the entire image and get back an aligned image. And we'll see that in the next section.
Okay, perfect. Yeah, I thought that was really instructive to go through that just single point case. And then, so like the last step here then is to actually apply the homography to the entire image. And there's a convenience function in OpenCV called warp perspective. And it takes 3 arguments, image 2, which is the scanned image of the form that we want to warp into the image 1 coordinates. That's the first argument. Second argument is the homography itself. And then the last argument is the dimension of the output image. And since both forms have the same, we're transforming an image of the scan form to the template, it's just the width and height of the template itself. We'll see that when we make panoramas, that we'll have to make an adjustment to that. But for this particular application, just using the width and height of the template form is sufficient. And so once we apply that and then display both images, you can see that we've warped the scanned form into image 1 coordinates, and it's almost a perfect match. You can see there's a little minor variation down here at the bottom right, but otherwise it looks like a very good alignment. And so would you like to, I know we're short on time, you want to switch over to the Panorama notebook?
Yeah, so let's switch over to the Panorama notebook.
Okay.
So we have learned about image alignment, and creating panoramas is very similar to creating aligning images. And one thing, when I mentioned that, homography relates the image of a plane to another image of a plane, there is one other condition when 2 images are related through a homography. And this is very interesting. If you take, let's say this is the camera, right? You take the camera, and about the center optical axis of the camera, you rotate it and take another photo. these two photos, when you rotate the image about its optical axis, rotate the camera about its optical axis, they are also related by a homography. And the scene doesn't need to be planar. So for a non-planar scene, doesn't matter what the scene is, it's a 3D scene. You're rotating the camera about its optical axis. And the two images you get, you take an image, rotate the camera about its optical axis, take another image. Those two images are also magically related by a homography, right? It can be mathematically proven, but like I said, in OpenCV for Beginners and other courses, we will not get into that kind of mathematical detail. We'll just tell you that homography relates two images taken in such a case, right? So here we have two images, and you can guess what we are going to do for creating a panorama. Bill, you can go ahead.
Yeah, sure. So notice that these two images, they overlap by a significant amount, maybe 50% or so, that this right-hand section here of image 1 is also over here in the left-hand side of image 2. And so this gives us an opportunity to find key points in both images so that we can compute the homography. So let's scroll down through this notebook. So this has already been executed, and it's the same, essentially the same exact code as the document alignment notebook that we just went through. So we're reading in both images. We're going to compute them to grayscale, compute the key points and descriptors, and then so let's display. So this is the set of key points for the first image, and if we scroll down here a little further, we'll see the key points for the second image. So notice that there are key points that are in the region that's not overlapping. But there's a lot of key points in the overlapping region, and that's going to help us find the homography. Notice also that the key points are concentrated in the region of both images that has the greatest texture. So those are very strong features associated with these bushes here on the horizon. Notice that there's no key points at all in the blue skies. There's almost no texture in that sky. And the grass has some texture. And if you look closely, you can see that there's some red circles down here in the foreground in the grass. So there's an opportunity for some features in that area, but predominantly the features are right along here where all the strong texture is in both images. And so, we had set this to a maximum of 500. If we had increased that to a couple of thousand, we might start seeing additional features. But this is plenty sufficient to create a panorama. So those are the two sets of key points. And then we're going to go ahead through the matching process. And now we're plotting the correspondences between the two images. And it's a little easier to see this if we scroll down here. I have a zoomed in section of that. So you can see this looks very clean, that clearly all these identified matches, we have all these parallel lines going back and forth between these two images are we've identified correctly corresponded key points in both sets of images. So this should be a very good result. And if we scroll down here further, here we're computing the homography. As Satya mentioned, the upper two right elements here are the translation portion of this, what's required to warp image 2 onto image 1. And if we scroll back, so let's take a look at that real quick. This is 320 pixels and 88 pixels. And so what that says is that this image is going to have to be warped and sheared a little bit and rotated, but there's a translation component to this that's going to shift the image to the left about 300 and shift it in one direction vertically about 80. And so let's take a look at the result, and we'll kind of pay attention to that a little bit. So here we're applying the warp perspective function on image 2. So we're passing it image 2 the homography. And in this case, the output image needs to be large enough to accommodate the width of both images, at least, or as a maximum, rather. So in this case, we're actually adding the two widths of both images. And so that's why we see this large black area here. It's going to accommodate putting both of these images side by side to some extent. But what we're looking at here is the image 2 that's been warped onto image 1 coordinates. And that's where that translation comes in. It's been warped and rotated and sheared, but there's a translation component of about 300, sliding to the left about 300 pixels. And when we stitch that together, this is the result that we get. So the way that the stitching works is that we're simply going to overwrite the overlapping pixels and just put these two images together in kind of a naive way with no additional sophistication about how to blend those two. If you look at the result here, if you look closely, you'll see that you can kind of make out a seam here in the middle of the where these two images were patched together. If you had, the reason for that is because when the camera's, taking the first image and then it's rotated and taking the second image, there's lighting changes and exposure differences. So you're going to see some differences due to that. And if you'd used a more elaborate stitching algorithm, you can usually blend that seam a little bit. But just with a naive aligning, it does a pretty good job just based on that. So I don't know if there's one last section here in this notebook we'd like to go through. But Satya, did you want to add anything to that so far?
Yeah, so in this notebook, we are just showing the geometrical aspect of it, not the photometric aspect of it, right? When image blending, that's a new topic in itself. There are various methods for blending images. Sometimes, people take averages between the two. Sometimes they find a cut. That minimizes, that passes through the pixels with least difference so that you don't see the seam. The pixels from the top to the bottom of the image, you find a cut in such a way that you don't see the seam. The cut passes through the pixels which have least difference, so you don't see the seam.
So not a straight line.
Yeah, not a straight line, right? It goes through the pixels with minimum difference. So that's it. But now are we ready to show
let's
all this
take a look.
hard work we have done? OpenCV makes it even easier, right? I mean, it's good to understand what goes on. It's also good to understand this thing because you can apply it to different things like image alignment. But OpenCV has a function called the stitcher class that Bill is going to show.
Okay, so let's take a look at that. This won't take very long because it's so easy to use. So so we showed an example above where we have two images. So now we're going to actually take 8 images from this folder here from that same scene. And we're going to use the stitcher class to put these all together in a panorama without all those details that we just went through. So here I'm just displaying the 8 images that we have on disk. And these were created in the same way, using a camera on a tripod and just panning the camera around and taking 8 photos sequentially. And they all overlap to some extent. And then what we can do is use this stitcher create class in OpenCV to create a stitcher object. And that gives us access to this stitch method. And all we do is pass in the list of images. And the result that we get back is the panorama itself. And so that's a beautiful and very simple way to create a panorama from multiple images. Obviously we have these black regions in here, and you could do some post-processing on that to detect the contour, for example, and maybe crop that out. But this just gives you a very convenient way to take any number of images and in one function call, get a panorama back.
Yeah. And Bill, if you have not recognized this is Del Mar Beach, which
I see that. I know. Right.
Okay.
Yeah.
And there is another way of finding these corners also. You can basically find the corner. You can find where all the corners of these images map. And based on that, you can make a determination. You don't even need to do contour finding. You already know where all the corners, the top left and the top right corners, similarly the bottom right and bottom left corners of each image ends up. So you know those coordinates, and based on that, you can make a very deterministic case of cropping out. You can calculate what the crop should be. So yeah, so that's it.
And I guess notice also that there's no seams, right? I mean, it has done a very nice job of blending all that together. So there's no evidence of any stitching.
So OpenCV
really
does all that automatically behind the scene with the stitcher class, right? But it's very important, to understand what's going on behind the scene, because you can use the same techniques in solving other problems, right? So that's about it from the presentation point of view, and we are ready to take questions.
Do we want to do trivia first or questions first?
Okay, we can do the trivia first. Go ahead, Phil.
You got the question. Go for it.
Okay. How many degrees of freedom does a homography have?
Wow.
All right.
You all were just
We already
Johnny
got
on the spot with that one.
I actually saw the answer before my question was complete.
Looks like Bhagawan Subedi is our winner here. I'll take a screenshot.
Wow.
Yeah, super quick on the draw.
Wow.
All right, so you will receive a free course for Computer Vision 1, and you will also receive OpenCV For Beginners, which we are running the Kickstarter campaign for it. But whenever the course launches, it's in September, you will get a free course for that as well.
Great, so let's do some Q&A, shall we?
Yeah.
First question here asks, will we share the Jupyter notebooks used here? The answer is yes. We'll make that all this code will be available to both people watching here and people who find it on our YouTube channel later. This will also be uploaded to YouTube, which answers the second question. It'll either be Friday or Monday. Our first real question is, what is the basis for picking key points in descriptors from an image? Like how does it actually work?
Okay, I will give you. I was actually hoping somebody would ask this question. Okay. Can you share the screen?
I gotta share it for you, right?
Yeah. Let me.
I'll stop sharing.
Okay. Yeah, let me share my screen. So I have this video. Now let's say, the features that we want, they need to have something that are easy to track, right? They are easy to identify, but they are also easy to locate. Now, what you're looking at is this black rectangle, and I'll show that we are looking at this rectangle through this hole. This is called an aperture problem in computer vision. So we are looking at this through this hole. Now let me move this.
Good for estimating the motion of the rectangle.
So if you move this, let me see.
So this too.
Sorry.
Well, how about
now if you move this thing?
Point is actually not good.
If you move the rectangle, you don't see any feature movement inside this circle. So you will never know that the rectangle actually moved because you're looking at it through this aperture. And this happens in computer vision all the time. When you're determining the key point, you're not looking at the entire image. You're looking at a portion of the image to determine whether this is a good point or not. So clearly, if a point doesn't have any features, it's not a good point. It doesn't have enough texture. So let's go over this point, right? What about a line feature? A line feature, let's say we have a motion in that direction, right? If you have a motion in the horizontal direction and you're looking through this aperture, you will never be able to find the motion because there's nothing changes in the image. Similarly, if you look at a vertical edge like that, it cannot determine the angle in the vertical direction, right? The motion in the vertical direction. But if it is a motion in the horizontal direction, you will notice it. So now this is obvious, right? It is obvious what kind of features are good. And the answer is
vertical are these
corner features, right? These features need to be like corners, right? They need to have change in intensity in both directions, right? In the X direction as well as in Y direction, so that they are kind of stable. They are used for motion estimation, but they are also used for matching, right? The more texture you have around the feature, the better the descriptor would be, right? So think about, a good feature is one that is stable when you transform the image, and it also has a lot of texture. So that's the easiest answer. Good feature has a lot of texture around it, right?
Yeah, that's great. Next question here is, throwing a wrench into some of the works. What if the camera has at different angles when taking images for a panorama? Like, how can you account for that and still get a usable panorama out of it?
Yes, to an extent. You can always estimate the homography that relates the two scenes. If things are very far away, your like when we do using a cell phone, we do this while doing a panorama, and it's not really about the optical axis, but things are so far away that it doesn't matter, right? And there are some more sophisticated techniques. They could have a slightly different sophisticated model, not just a simple homography, but a slightly more sophisticated model, and they estimate the parameters of that model instead. But if the scene is far away, then even if it is not exactly along the optical axis, the approximation would work.
Cool. Next question. What if you don't have very much of an overlap between some of the images that you're trying to stitch together? How much do you really need, or do you need any if it's from a similar perspective, same camera, etc.?
So you need 50% overlap. You can be very sure that you will get good features if it's a natural scene, right? If it is all white, then nothing helps, right? The other approach, suppose you don't have any overlap for whatever reason, then you need a calibrated camera setup. You need to know where these cameras are looking, right? That's by tracking features, we are doing not exactly camera calibration, but we are trying to figure out where the cameras are looking by tracking features. But if you don't have that, but the calibration between the cameras, and this is a rigid setup, then you can do stitching as well.
Thanks. Let's see, we got time for a couple more. Next question is for edge or like deeply embedded stuff. OpenCV might not be available. They might not have the compute for it, or the space, or the money even. What would you suggest for using this kind of technology when OpenCV is not necessarily available?
You can extract the code from OpenCV and make a very lightweight version of it. The algorithms for feature matching, they are actually feature detection. They are very fast. In fact, the ORB feature is, it's extremely fast, computationally very inexpensive. So you can run it on very lightweight hardware as well. And just a trivia, the guy who invented ORB feature, Ethan Rubley, I talk to him on a weekly basis. We work on some projects. So it's an OpenCV function, ORB. The people at OpenCV actually invented that.
It's a small world, computer vision. We're trying to make it bigger. That's I think we've got time for one more here. Any recommendations on books if some of the viewers want to do a deeper dive on some of the math involved here? I know we've been talking a lot about CV for beginners and not going into the math, but I know there's some people watching who might be more interested in the actual, solid math behind this. Do you have any suggestions for books or
so there is a book by Richard Zaleski. He was head of Microsoft Computer Vision Lab for the longest time, Microsoft Research. It's called Computer Vision by Richard Zaleski. It has a very broad overview of a lot of techniques. It goes into math on panoramas, etc. also.
All right, we'll do one more real quick, which is, is there a minimum resolution for these images to make it viable to do this kind of matching and stitching?
It's very difficult to say, right? You could have a low resolution image, but if the texture is very high, the matching will still work, right? You could have a very high resolution image of something which is very smooth, and then you cannot even do matches and things will fail. So it depends. Basically, you have to, the right question is there enough texture in the scene to do the matching?
Awesome. I think that's all we got time for today. You want to take us home, Satya?
Okay, thank you so much for joining on this webinar, and tell us, in our feedback, tell us whether you like this format. We bring in people who discuss at a high level, but this is a very beginner's kind of guide. Tell us if you like this format, we'll do more of these. And if you have not looked at our Kickstarter campaign, please go and hopefully back it. Tell your friends and family, colleagues about it. we'll be really grateful. It helps support the library and all the free stuff we do, including this webinar. And thanks, Bill. Thanks, Phil. Really grateful for everybody who showed up today. Thank you.
Thank you. Thank you.
Yeah, thank you, Satya. Thanks, everybody else. As a reminder, we do this every Thursday morning at 9 a.m. If you came in late today, you can join us early next week.
I just wanted to mention, this is the, in case you guys missed it, this is the actual book that Satya was referring to, and it's also the book that's featured in that document alignment notebook, right? So it's the same book, so I thought I'd just toss that up there.
That's right. I forgot about
That's awesome.
that. Okay.
All right. Thanks, everybody.
All right. Thanks. Bye.
Thanks. Bye.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. Today's episode was brought to you by OpenCV Courses. Back their new Kickstarter campaign, OpenCV For Beginners. Find out more at opencv.org/courses. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.